In this session, we will discuss about the power MOSFET. Okay, in the previous session, we studied about the BJT. So, BJT is a current controlled device and requires base current for current flow in the collector. Okay, because the collector current is dependent on the input or base current. The current gain is highly dependent on the junction temperature. Okay, but here the power MOSFET is a voltage controlled device. Okay, so it is a voltage controlled device and requires only a small input current. Then the switching speed is very high and the switching times are of the order of nanoseconds. Then power MOSFETs find increasing applications in low power, high frequency converters. Though the power MOSFET has these positive sides, okay, including this, that is, the power MOSFET does not have the second breakdown phenomena as in BJT. Okay, in BJT there is a second breakdown, but in power MOSFET it is not the case. Okay, though these positive sides are there in power MOSFET, there are also negative sides. Okay, the problems are MOSFETs have the problems of electrostatic discharge and require special care in handling. In addition to that, it is very difficult to protect under short circuited fault conditions. Okay, so this is the general introduction about the power MOSFET. So it is a symbol of power MOSFET. It is a 3-terminal device. The terminals are drain, source and gate. Okay, here the arrow indicates the direction of the current flow. So MOSFET is a voltage controlled device. The operation of MOSFET depends on flow of majority carriers only. Okay, then the gate draws a very small leakage current in the order of nano ampere. Now we can see the basic construction. So see here, so it is a planar metal oxide semiconductor structure for N-channel p-MOSFET. So there are two types, N-channel p-MOSFET and enhanced MOSFET. Okay, enhancement MOSFET, but here in this session we will study about this N-channel p-MOSFET. Okay, so the bottom layer, okay, the bottom layer is N plus substrate. On this substrate, a high resistivity. So this is the N plus substrate. On this N plus substrate, there is a high resistivity N minus layer. Okay, which is grown epitaxially upon this N plus region. This N minus region is called drift region. Okay, so this region is responsible for the breakdown voltage of the device. On the other side of this N plus region, okay, this is the other side of this N plus substrate. So here a metal layer is deposited to form the drain terminal. Okay, this is the drain terminal is formed here in this region. Okay, then P minus, so this is the P minus region. Okay, so this is P minus. So P minus regions are diffused in the epitaxially grown N minus layer. Okay, so upon this N minus layer there is a P minus region. Then upon this P minus region there is a N plus region. Okay, N plus region is diffused in the P region. So then upon this N plus regions there is a layer called SiO2. Okay, silicon dioxide layer is added and it is etched so as to fit the metallic source and gate terminals. Okay, to form these source and gate terminals, this SiO2 is etched like this. Now we can see the operation. So when gate source voltage is 0, okay, we are not giving any supply to this gate source voltage, but the source voltage is present. Okay, VDD is present. Then n minus p minus, okay, this is p minus as I said already. So n minus p minus regions are reverse biased. So no current flows from drain to source. Now the device is considered as a open switch. So when the gate terminal is made positive, okay, first we didn't give the supply to this gate source voltage, gate source, but here now we are going to give the positive gate signal, okay, gate terminal is made positive with respect to source. So what will happen, an electric field is created, okay, electric field, see here, an electric field is created and electrons, see here, electrons form n minus channel in the p minus regions, okay, upon this p minus regions there is a n minus n channel, okay, n channel is formed. Now, so because of this what will happen, there will be a current flow, okay, a drain source, sorry, drain current, okay, there is a current flows from drain to source. From drain to source there is a current, okay, which is indicated, okay, by the arrow. So when the gate source voltage is increased, okay, now we are going to increase this voltage, then what will happen, this drain current also will increase, okay, that's why this power MOSFET is called as voltage controlled device. So why the power MOSFET is called as voltage controlled device? Since the output current is controlled by the gate voltage, it is called as a voltage controlled device, okay, it is important. So here the controlling parameter is gate source voltage, okay. Now we can see the characteristics of MOSFET. So there are two characteristics, static characteristics and switching characteristics. First we will study about static characteristics. So in that we are going to learn about transfer characteristics and output characteristics. This one is transfer characteristics and this one is output characteristics. So first one is transfer characteristics. It is drawn between the drain current and gate source voltage, okay. So from this what we can understand is there is a threshold voltage, okay. So there is a threshold, this is the threshold voltage, gate source threshold voltage. Below this voltage the device is off, okay. Only when the voltage reaches this threshold value, then the device gets on, okay. Below that value it is off. So this VGST value is in the order of 2 to 3 volt, okay. It may be in the 2 to, this VGST may be in 2 volt or 3 volt or in between any other values. Then output characteristics. So it is drawn between the drain current and drain source voltage, okay. Here VGS is the parameter, okay, controlling parameter. So see here, see this characteristics curve for low values of VDS, okay. For low values of VDS, so is this here the VDS is 0, for 1, so this is the value, for 1.1 this value, 1.2 this value. So if for lower value the characteristics curve is linear, okay, this curve, okay, this is the linear curve for lower values of VDS, okay. So this indicates a constant value of on resistance, that is RDS is equal to BDS by IDS, okay, V by voltage by current. Then for a given VGS, it may be 0 volt or 1 volt or 2 volt, any volt we can take, okay, as constant. For example, first we will take VGS is equal to 0, okay, for 0 volt. If we increase this VDS, that is drain source voltage, what will happen, okay. So we keep on increasing this VDS. What about this ID current? No change in the ID current, okay. So the characteristics curve is almost flat, okay. In the same way, if VGS equal to 3 volt or 4 volt, okay, then also if we keep on increasing this VDS, it is increasing but no change in the drain current, okay. The curve is almost flat, okay. So this is the output characteristics. So this is the load line which intersects the point A and B. Then we will study about switching characteristics. This is the switching characteristics curve. Okay, so the switching characteristic is influenced by two factors. Okay, what are they? Internal capacitance of the device and internal impedance of the gate drive circuit. Okay, these two are important. Internal capacitance of the device and the internal impedance of the gate drive circuit. Okay, now we will see about the turn on time. Okay, because switching characteristics means the turning on and turning off process. Okay, what will happen? So in turn on time there are two periods, that is turn on delay time and rise time. You will see one by one. So turn on process, this is a sum of turn on delay time and rise time. Okay, so what is turn on delay time here? So this is TDN. Okay, this period is called turn on delay time. So in this period the input capacitance charges to VGST. Okay, the input capacitance charges to VGST. So this period is called turn on delay time. Okay, at the time, at the same for the same time the ID current is 0. Okay, so during the turn on delay time, so VGS rises to VGST and ID is equal to 0. What will happen in rise time? Okay, so in rise time the voltage gate source voltage rises from VGST to VGSP. Okay, it is the gate source peak voltage. Okay, it is the gate source peak voltage. So this voltage is sufficient to drive the MOSFET into on state. Okay, now at the same time, what about the ID current? So it rises from 0 to the full value. Okay, full value, that is ID. Okay, it rises from 0 to ID value. So that total turn on time is equal to the turn on delay time and plus turn on rise time. Okay, so this turn on time can be reduced by using low impedance gate drive circuit. Next one is turn off process. Okay, so we have studied about turn on process. Now in switching characteristics, the next one is turn off process. Okay, so this is turn off process. So it is initiated by the removal of the gate source voltage, because when we give the gate source voltage, the device gets turned on. Okay, if we remove the gate source voltage, then it should be off. Okay, so by removing it, see the time interval t1, at time t1, okay, this VGS, what will happen? This VGS, the voltage, okay, gate source voltage reduces from V1 to VGSP. Okay, so this so it will come in the next slide. So first, what is turn off process? There are two time periods, that is TDF and TF, that is turn off delay time and turn off fall time. Okay, the summation of these two periods is called turn off time. Okay, so first one is turn off delay time. So in this time, what will happen? The voltage, gate source voltage decreases from V1 to VGSP, that is peak gate source voltage. Okay, from V1 to VGSP it reduces. Okay, but the drain current is constant. Okay, there is no change in the drain current. It is the turn off delay time. Then next one is fall time. Okay, that is TF. So during fall time, the input capacitance again discharges from VGSP. Okay, from VGSP to VGST. From this value again it is reduced. Okay, then what about drain current? So at that time the drain current has reached 0 value. Okay, the drain current falls from ID to 0 value. So when VGS, that is gate source voltage, is less than or equal to VGST, that is gate source threshold voltage, the power MOSFET turn off is complete. Okay, so if the power MOSFET is if you want to turn off the power MOSFET, then the gate source voltage should be less than or equal to VGST. Okay, so the complete turn off time is equal to turn off delay time plus turn off fall time. Finally, we can see the comparison between MOSFET and BJT. Okay, power MOSFET and power BJT. So MOSFET has lower switching losses, BJT has higher switching losses, MOSFET has more conduction loss, and BJT has low conduction losses. MOSFET is a voltage controlled device, whereas BJT is a current controlled device. MOSFET is an unipolar device, and the BJT is a bipolar device. Okay, MOSFET operates at switching frequencies in the range of megahertz, but BJT it operates in the range of kilohertz range of frequencies. Okay, then a MOSFET has positive temperature coefficient, whereas BJT has negative temperature coefficient. There is no secondary breakdown in the MOSFET, but in BJT there is a secondary breakdown. Okay, then MOSFETs are available with ratings up to 500 volt 140 amps, but the BJTs are available with ratings up to 1200 volt and 800 amps. Okay, so these are the comparison of MOSFET and BJT. Okay, so these are all about the power MOSFET. Thank you.